Welcome to physics. Today we're going to go a little deeper into problem solving. So we're going to start with an example here, and then we're going to get into some applications. So this is actually a problem that is on the worksheet, problem number 20. You have a diagram of the human eye that's looking at an ice cream cone, and you can see how the light goes through the lens and the cornea and forms an image on the retina. So if we're solving this one down, the first thing we're going to want to do is identify what the given information is. So on your diagram, we have the 14 centimeters. That's related to the object. That is the height of the object. You have the 35 centimeters, which would be your distance from the lens going out to where the object is. So that would be D sub O. You have the 17 millimeters. That's the distance from your lens and cornea system to the retina, which is where the image forms. So that would be D sub I. That is given in millimeters. I'm going to convert it into centimeters, so that would be 1.7 centimeters. Always check to see if you have conversions to do. Last thing we know, by looking at the shape of the lens in the eye, right there, we can see by that shape that that is a converging lens. Now we have the given information. So first thing we want to find is the focal length. So 1 over f equals 1 over d sub I plus 1 over d sub O. So this is going to be 1 over f is equal to 1 over our d sub I value, 1.7 centimeters, plus 1 over 35 centimeters. If we solve this down, 1 divided by 1.7, that's going to give us a value of 0.588. 1 divided by 35, that's going to give us a value of 0.0286, and we can combine those together. So that'll give us a value of 1 over f is equal to 0.6168, rounding a little bit. So then our focal length, 1 divided by that number, is going to give us a 1.62 centimeters. Part B, we want to know what the image height is. We can use our second equation. Hi-ho equals negative di del. So h sub I over 14 centimeters is equal to negative d sub I was 1.7 centimeters. And d sub O is 35 centimeters. So if we cross multiply and solve down, that's going to be 14 times the negative 1.7 divided by 35. That's going to give us an image height of negative 0.68 centimeters. In part C then, we want to calculate the magnification. When you're calculating magnification, that's comparing the image to the object. So then we can either do d sub I over d sub O or h sub I over h sub O. We know both of them. It really doesn't matter. So if I go with our distances, 1.7 centimeters divided by 35, and that's going to give us a magnification value of 0.05. That means that the image is going to be reduced in size because you have a magnification less than 1. So the image is just a fraction or a decimal of the object size. So now let's get into refraction and the physics of the human eye. So I've got two diagrams over there to the side. Top one, kind of an overview. The bottom one, some of the more specific parts. We're not going to focus on all the biology. Rather, we're going to focus on the parts of the eye that are relevant to the refraction and to how you see. So the pupil and the iris. Pupil, it's not a thing, it's a hole. It is a hole in the iris, and the iris is the colored part of your eye that surrounds the pupil. The pupil being a hole, that's where light goes through. So that is how light enters your eye to be able to form an image. Your iris then, the colored part, will control the size of the pupil. When it's dark outside, then the iris will spread and allow the hole to become larger and allow more light in is seen in the picture in the lower left. The lower left eye is normal, and then the one just to the right of it, the pupil is dilated. When it's very bright outside, then the iris will close in and make the pupil smaller so that not too much light gets into the eye. Next two parts, the lens and the cornea. On the diagram below, and I'm going to highlight a little bit, your cornea is overall this entire part of the eye, and then the lens would be that part that I'm highlighting right now. Your lens and cornea both have properties to be able to refract the light. If you look at the shape of the cornea and you look at the shape of the lens, they are both in the shape of a converging lens. So both of them serve as or take on the role as a converging lens. They both refract the light. The cornea does actually most of the refracting of the light. In other words, it gets the light traveling in approximately the right direction for you to be able to see. Then the lens does more of the fine focusing of the light to be able to get a clear, crisp image that forms on the retina at the back of the eye. Both parts are needed. Both parts have separate roles. If your cornea is not working correctly, you can't see clearly. If your lens is not working correctly, you cannot see clearly. Now on to the retina. That is the yellow along the back of the eye, and I'm going to try to highlight in green here along the edge. This right next to the green line that I'm putting all the way around here, that is your retina, just to the right side or above or below that green line that I put. The retina is basically where the light focuses to be able to form an image. Your retina is where you have rods and cones, and these rods and cones convert the light into an electrical signal, and then this electrical signal is carried to your brain by the optic nerve. Your eye does not see. Your eye refracts the light. The light then focuses on the retina. The retina then converts the light into an electrical impulse that then goes down the optic nerve to the brain, and then your brain gets this signal and has to make sense of it. When it makes sense of it, then you see. So then sight occurs in the brain. The eye is only the thing that is receiving the light, receiving the signal. One other thing I wanted to hit here, and that is your ciliary muscles. And your ciliary muscles are basically above and below the lens, and they will stretch and they will change the shape of the lens. Ciliary muscles connected to the lens pull, push on that lens to be able to change its shape. In changing the shape of the lens, they allow you to focus on things that are near and far away. You can look at something in front of you. You can look across the room at something more distant, and the ciliary muscles are working to change the shape of the lens to be able to change the focal length of the lens so that that image can still come into focus clearly. Now, you're all very young. Your ciliary muscles are working pretty well. When you get into your 40s, those ciliary muscles start to atrophy. They no longer work as well. The lens loses some of its elasticity. The combination of that is you can't change the shape of your lens as easily. You are most using your ciliary muscles when you are looking at something close. So if you are watching lots of videos, reading lots of books, your eyes get tired when you are looking at something close. When you hit your early 40s, then those ciliary muscles start to atrophy. So maybe parents, people you've seen, you see them when they start to read something, they'll start to move it further and further away from them to be able to see it clearly. They have hit that point where the ciliary muscles are no longer working right. The lens has lost some of its elasticity and they lose the ability to focus on things close. That's when you get reading glasses. So overall, these are the parts of the eye. I want to return to this image for just a moment and take a look at the retina, which is in the top left corner. That retina is pretty darn complex. If we look at it in comparison to a camera, an iPhone 11 camera, 12 megapixel camera, the human eye with all the rods and cones equivalent to 576 megapixels. So technologically, we cannot create anything that is anywhere near what the human eye is. Something to ponder. Now what we want to get into is the actual process of seeing. So what we're going to get into here is more of what the light is doing. So I'm going to draw a diagram here. Here you are, not to scale. I'll put an eye there in a second. Okay, so let's say you are looking at a tree. Light is going to come from that tree, and I'm not going to draw the actual rays, but light is coming off of that tree and going into your eye. Let's add your eye here. No, it's not going to be to scale. I need a little bit of shape, but you're very happy here. So here is your eyeball, and what the light is going to do is go through the lens cornea system and refract and form an image on your retina. When it forms that image on the retina, I'm drawing in red, that image that forms on the retina, it must be real. You cannot activate the rods and cones if you don't actually have light there, so it must be real. We can tell based on the size of the actual tree and the size of your eye, that image is reduced in size. And it is also inverted. Real we talked about. Let's talk about the inverted. There is an upside down image that forms on your retina, but your eye is not where you see, so then that signal goes to your brain. So from your retina, that signal is going to your brain, and your brain has to interpret that image. Now, if you saw everything upside down, but then with hands and feet felt everything right side up, there would be a sensory conflict in your mind. So then your brain's going to resolve that, and it's going to flip the image over. So then even though the image forms on the retina, reduced and inverted, your brain will actually process that signal, and the brain flips the image over so that you see things right side up and life size, not reduced in size. So in a very, very simplistic diagram, lacking all relevant size and biology, there's our tree, light going through the lens cornea system, the image forming inverted on the retina, and then the brain flipping that back over. That's all for today on the human eye. Some of the problem solving will get into applications of the human eye and even a little bit on nearsighted and farsighted. Next time we will get into depth perception and more applications with the human eye.